welcome to Aaron Bernstein, who is joining us from Rutgers. Aaron is arguably the expert on things like shortest paths and matchings in models like dynamic graphs and online computation. And Aaron is, as I said, a professor at Rutgers, and he's won several Best Student Paper Awards, I think at Stock and Fox, and Best Paper Awards at SOTA and iCalp. And today he's telling us about a very nice recent result, a near linear time algorithm for negative weight single source shortest path. So thank you, Aaron. And let me say to everybody in the audience that at chat, you can always post questions there. I'll pay attention to it and point out if we have questions there.
Okay, Rasmus, thank you so much for the introduction. Hi, everyone. So I've never used AirMeet before, so there are technical things like slides aren't showing up or whatever, but I think it should be fine. Okay, yeah, so I'm going to talk today about a near linear time algorithm for single source shortest paths in a graph with negative weights. And this is joint work with Danyapon Nanan, moving between many places, and Christian Bolt-Nilsson. Okay, so let's start by introducing the problem. Classic problem, you have a graph, source, you want to compute a shortest path tree from the source. So there are kind of the classic algorithms for this. And the main takeaway is that if the graph is unweighted or has non-negative weights, this problem is easy. But once you introduce negative weights, the problem gets much, much harder. So let's talk about the history of this case where you have a graph with negative weights. So you have a directed graph, a source S, and you want to output a shortest path tree from S. Or if there's a negative weight cycle, you want to output that. So the problem is that there's this classic MN time algorithm, Bellman-Ford, and this is actually still the best known if your weights are totally arbitrary. So basically, strongly polynomial time algorithm, MN is the best we know. And for this reason, all future work has focused on the natural setting of assuming you have like integral edge weights that are polynomial in N. And in this case, you can do better. And so I want to briefly talk about the history of the problem. There are basically three phases. There's the first phase of like the kind of classic algorithms, and this gets MN. And then in the 80s and 90s, there's kind of a combinatorial improvements. And these go down all the way to M root N. And for a long time after this, people were stuck. I mean, people kept working on this problem, wondering if M root N is the best, but all progress seemed to stall for many decades until extremely recently. There is a new series that actually managed to break through this barrier, first for sparse graphs and then for dense graphs. And this is based on an entirely different set of techniques that uses continuous optimization. And the most recent ones, the most efficient ones, are also using a lot of dynamic data structures, such as dynamic expander decomposition. So a question you might ask, well, there are two natural questions. One is, of course, can you do faster? And a second result is, or a second question is basically whether or not these sort of the most recent results are using quite heavy machinery, and they're generally solving a much more general problems. And it's sort of unclear, like for a problem as specific as negative weight shortest paths, you know, it's such a simple problem to define. Do you really need this kind of heavy machinery? Or is it possible to actually make progress on this problem using the kind of more standard, simpler combinatorial approach? And so we answer both of those in the informative. We show an algorithm that's near linear and kind of follows the more basic combinatorial tools of the 90s. Okay, so I also want to talk about in a result that was done independently of our work that's super relevant. So our result is we get M polylog time for negative weight single source shortest paths. And at the same time, there was another result by several people who are here at ETH that solves min cost flow in almost the same time, slightly slower. And in particular, min cost flow is a much more general problem. So this implies a result for negative weight single source shortest path, but also for many other graph problems. So this is a huge breakthrough in graph algorithms because there are lots and lots of problems where we didn't know how to solve them until this min cost flow result. And so, as I said, our two results were done independently, but now that we have this fast min cost flow algorithm, I kind of want to talk about how I think about our result for this more specific problem in light of the min cost flow algorithm. So to kind the perspective a bit, I wrote down a list here of some like fundamental graph problems, such as like shortest paths with negative weights, bipartite matching, ST-cut. So these are all problems that are kind of at the core of graph algorithms. We tend to teach them on undergraduate algorithms. They've been around for many, many decades. They come up a lot in practice. But surprisingly, even though they're so fundamental to the field, they also turn out to be very hard. And in particular, for a lot of these problems, for many decades, we had no idea what the right running time was. And so the really cool thing with this recent result on min-cost flow is that it showed that actually, yes, you can solve all these problems efficiently in almost linear time. But I think a question that remains now that we know the complexity, or now that we know the running time, is that basically, can we devise simpler algorithms for these problems? So currently, the way to solve all of these problems is basically by solving the much more general min-cost flow algorithm using heavy machinery. And that's really the only way we know how to approach them. So in particular, I said for negative weight shortest paths that progress stalled in the 90s, and we weren't really able to do anything beyond that. And that's kind of true for all of these problems. If you think about it, like bipartite matching, max flow, like the standard approach is all stalled a long time ago. And so I think a question that comes up then is, to what extent do we need heavy machinery? Or by contrast, is it possible to develop simple algorithms for some of these problems? Now, obviously, simple is kind of a judgment call. So, as I said, the authors of the min-cost flow paper are here. You can ask them, maybe they'll have a perspective. I think they would agree sort of the most recent min-cost flow algorithms are very impressive, but also very complicated and use a lot of heavy machinery. And so it's interesting to ask to what extent we need this machinery. And I think that the simplicity, there are sort of two reasons why I think it's especially important for these problems. One is just that because they're such fundamental problems, and many of them are so easy to state, something like shortest paths or bipartite matching, it'd be nice to have algorithms that you could teach to a beginning graduate student, or you could maybe implement. So that's one reason for the focus on simplicity. A second reason is that for a lot of these problems, we also implement other models, such as distributed algorithms or parallel algorithms. And in order to be able to port the kind of ideas from sequential algorithms to these parallel algorithms, that's going to be hard if you're with the heavier machinery that you use. And so in particular, I think, we don't have any actual results, but I think if you look at our result from this talk, you'll see that it's the kind of thing that I think is more likely to be able to be ported into something like distributed or parallel settings. Okay, so that's the problem and the motivation. So let's talk about the actual result. Let's start by some basic preliminaries that we need to get our result. So first off, some simplifying assumptions. So we're going to assume that the graph has constant degree, that all the edge weights are integral, and that all negative edges are exactly -1, and that the graph doesn't contain a negative weight cycle. This is actually without loss of generality. We show you can always reduce to this case. The reductions are pretty simple. They basically use folklore. I think the nicest part is the step 3, basically show that any algorithm that works assuming there is no negative weight cycle can actually be used as a black box to detect the negative weight cycle if it does exist. So that's just kind of a nice quality of life thing where we can always, without loss of generality, focus on the case of no negative weight cycle. Okay, so now talking about the preliminaries. So I should say that somehow, in some sense, because this algorithm is simple, I'm going to try a complicated thing where I'm essentially going to tell you the whole algorithm from start to finish. So some of the slides might be a little more technical, or there might just be algebra. So please, especially here, like if you don't understand something, it's because I'm explaining it badly. So you should definitely stop me if there are any questions or something doesn't make sense. Okay, so one of the most basic tools to deal with negative weights is called price functions. I mean, these are very old, I think from the 70s. And so I'm just going to very quickly kind of review them. So given a graph and a price function on the vertices, you can define what's called the reduced graph, which has the exact same vertices and edges, but different edge weights. And in particular, the reduced edge weight is just the original edge weight, WUV, plus the price of U minus the price of V. And so this is just like an easy graph transformation. And the reason that it's so useful is because it was proved that shortest paths in G and this reduced graph are the same. Adjusting by prices never changes the shortest path structure. And the proof is quite easy. It's based on this claim that basically given any path from X to Y, the weight of the path in the reduced graph is always the original weight in the original graph plus 5X minus 5Y. And the reason is just this telescoping sum, that basically if you look at some edge, say from X2 to X3, then the reduced weight adds 5X2 and subtracts 5X3. So basically whenever you enter a vertex, you subtract its price, and whenever you leave a vertex, you add its price. And so for all the vertices in the middle, all of the prices cancel, and only the price in the beginning and end matters. And so what this means is that if you look at any two paths from X to Y, in the reduced graph, they're all being shifted by the same additive amount, 5X minus 5Y. And so whatever path was shortest in the original graph will still be shortest after this shift. Okay, so that's. So we also want to talk about computing price. So again, you can set any price function you want and do this transformation, but really the goal is we want to compute a price function such that these reduced weights are all non-negative. If we can do that, then we've solved the problem, because then we can just use Dijkstra to compute a shortest path tree. And the point is that that shortest path tree will be the same as in the original graph because prices don't change shortest paths. So it's well known that there exists a price function such that all the weights become non-negative, assuming the graph doesn't have a negative weight cycle. And so here's the proof that such a price function exists, which is take your graph, create a dummy source. So it's just a source with edges of weight 0 to every vertex, and then set the price of a vertex to be the distance from the dummy source to that vertex. I'm not showing you how to compute those distances, but those distances exist. And if you set that to be the price, then all of your weights will become non-negative. And the reason is literally just triangle inequality. So the reduced V becomes the original weight plus the distance from S to U minus the distance from S to V. By triangle inequality, this is not negative. So the takeaway here is that if we have a function that's good, meaning all the edges are non-negative, it's easy to compute distances using Dijkstra's. And similarly, if we can compute distances in the original graph, we can use those distances to set a good price function. So somehow these two things are kind of interchangeable, and we're going to be constantly using both. We're going to slightly improve our price function to get slightly better distances, to get a slightly better price function, and so on and so forth. Okay, so this is the first ingredient. And I also want to highlight here that, right, in order to figure out the price function, we introduced this dummy source. And for that reason, basically all of our algorithms, all of our auxiliary algorithms are actually going to be running from a dummy source. We ignore the input source for 99% of the algorithm and just deal with dummy sources. So whenever you see source S, you should not be thinking the original source from which we want the shortest path tree. You should be thinking S is a dummy source. Okay, so that's the first ingredient we're going to need is price functions. The second ingredient is, it turns out that negative edges are the hard part, right? If we only had non-negative edges, then we could just run Dijkstra and everything would be easy. And Bellman-Ford, we know if you have negative edges, it takes Mn, but also Bellman-Ford implies something stronger, which is that if every shortest path contains at most gamma edges, then the running time of Bellman-Ford is M gamma. You just stop after gamma iterations. So in fact, you can say something stronger. Lemma Bellman-Ford plus Dijkstra, which basically says that if you have the property that all of your shortest paths contain few negative edges, at most k negative edges, but as many positive edges as you want, then the running time is mk. I have no idea if this algorithm is new to our paper. I think it's folklore. So the algorithm is extremely simple. Basically, you start with a source, and first you only explore the non-negative edges. And so you just run Dijkstra's. And this gives you the shortest path with 0 negative edges. And then you just take all the negative edges and you run a single iteration of Bellman-Ford, meaning you just sort of relax each negative edge once. You like adjust the labels on each negative edge exactly once. And so that's going to give you the shortest path using as many non-negative edges as you want, and then one negative edge. And now from those labels, you just run Dijkstra again. And that's going to explore all the non-negative edges. And now you have the shortest path using non-negative edges, then one negative edge, and then many non-negative edges. And then again, you run Bellman-Ford, and you just sort of for one iteration. And by just layering these, you get that as long as the number of negative edges is less than k, your running time is mk. So that's a basic algorithm we're going to need. And we actually prove a generalization. And the generalization is that you don't need the statement that every vertex has few negative weight edges on the shortest path for this to be true of the average vertex. And that's good enough. And this is exactly proof. You just combine Bellman-Ford and Dijkstra. For this statement to be true, you need the assumption that G is constant degree. Okay, so but what you should remember is that as long as there are few negative edges on shortest paths on average, it's easy to compute distances. So how are we going to combine this with prices? The idea, the very high level idea, is we have this algorithm that works well if there are few negative edges. And we said our final was to compute a price function such that all edges become non-negative. And the way to achieve this final goal is we're instead going to achieve an intermediate goal. We're going to use this function, which still leaves some negative edges, but only few of them. And in particular, it's going to ensure that in a reduced graph, on average, shortest paths have few negative edges. And I claim if we can get this intermediate goal, then we can get to the final goal. Because now all we have to do is, now we have this graph that has few negative edges on average. So you run Bellman-Ford plus Dijkstra to compute distances from a dummy source in this graph. And now, as we said before, if you can compute distances, then you can actually compute the final price function with non-negative edges. So this is what I meant when I said you first compute a pretty good price function, then you use that to compute distances, and then you use those distances to compute a really good price function. Okay, so those are kind of the two easy preliminaries that we use. Those are kind of just from basic shortest path tools. So there's one slightly more complicated existing technique that we need, which is low diameter decomposition. So I need it here, and I'm going to state it first for undirected graphs. In the end, we're going to need it for directed graphs, but it's more intuitive for undirected graphs, so I just want to start there. So here's the claim. You're given an undirected graph with non-negative weights. It's very important this only works for non-negative weights. And some positive integer d, some parameter. And what you can do is you can take your graph G and you can decompose it. You can basically decompose it into small connected components plus some crossing edges. So the property is that each connected component is going to have diameter at most d, weak diameter at most d, and there are few crossing edges. These crossing edges, those are the edges in ESEP. And when we say few, we mean something pretty strong. It's not just that the absolute number of crossing edges is few, it's that any particular edge has a small probability of being one of these crossing edges, of being a separator edge. And the probability is basically the weight of the edge divided by your diameter d. So let's have a picture. So basically, you start with your graph G, the black ball, and you can decompose it into these green components such that each component has weak diameter d. So meaning for any two vertices in the component, there's some path of length at most d. That path might leave the component. That's why it's weak diameter. But still, there's a short path between any two vertices in the component. And then you have these small number of crossing edges, and each vertex has a small probability of being one of these red edges. Okay, so this is very much not new to this paper. There is a huge amount of previous, starting from the 80s. And there are many different variants for this problem, depending on the setting you're working in, depending on exactly what parameters you want, whether your graph is weighted or unweighted. So there's like a whole bunch of prior work, and I'm only familiar with a small section of it. But it all kind of uses similar techniques. And in particular, the statement I have above is definitely something that was known before us. Like that exact statement was known. And in fact, it's known how to compute it efficiently in, for example, distributed settings. So the decomposition itself is not new to our paper. I think what is new is how we use it. And in particular, ours is the first result to apply this decomposition to negative weights, which is sort of unsurprising because decomposition only works for non-negative weights. So it's unclear at this stage how we're even applying it to weights, but we'll show it's surprisingly useful. And this I'm less sure of, but as far as I know, surprisingly, I have never seen decomposition used in the like regular static setting. I've seen it used a ton in distributed and parallel algorithms and a few dynamic algorithms, but I've never just seen like a normal static algorithm that uses this decomposition. I might be wrong, and if you know of a counterexample, I would love to hear it. Okay, so this is the decomposition. Let me just give a very quick outline mostly just to give an intuition for where these bounds are coming from, and also to kind of make it clear that there's nothing fancy going into this decomposition. The high-level algorithm is actually extremely simple. All you do is you arbitrary source, and you grow a ball from that source up to some random threshold tau between 0 and d. And then all of the edges on the boundary, so the edges, the vertices between like that are more than distance like tau but less than the next distance, so they all become separator edges. And so in particular, once you add those separator edges, you're sort of disconnecting this ball. And that ball has small diameter, so that's fine. That becomes one of your small diameter connected components. And now you just repeat in the rest of the graph. You pick another arbitrary source, you again grow a ball up to a random threshold, add everything to the boundary, to the separator edges, and so on. And the basic intuition is that if you look at any particular edge, because you're picking a random threshold between 0 and d, the probability that that edge gets cut is at most 1 over d. And so that's why the probability that an edge is a separator edge is 1 over d in the unweighted setting. But of course, if it's a weighted edge, if it has length 100, then it's 100 times more likely to be cut. And so that's why the probability that an edge is a separator edge is the weight of that edge divided by d. So I'm kind of skipping a few details of exactly how to make you have to be a little careful with the randomization. It's not a uniform threshold. It's like a geometric distribution, but this is the basic algorithm. Okay, so as I said, though, we're going to need this for directed graphs. So this was the decomposition for us. Let's move on to directed ones. So in directed graphs, it's a statement. So again, we're given a directed graph, non-negative weights, and some parameter d. And there exists a fast algorithm that, again, is going to compute a set of separator edges such that once you have separator edges, all SCCs have small weak diameter. And that means in both directions. So let me show the picture. What we're saying is you have your graph, and I'm going to remove some separator edges. Those are the red edges. And my guarantee is that after I remove those separator edges, if I now compute SCCs in this graph, those are these green SCCs, then each one has small weak diameter. So you can see you have two pink vertices, the distance between them is at most d. Now, if you think about this graph minus the red edges, any directed graph can be decomposed as a bunch of SCCs and then a bunch of DAG edges on top of those SCCs that all move in one direction. So that's why I drew here, basically the green SCCs are in topological order and the black edges all move forward. So if I remove the red edges and I decompose into SCCs, this is what I get. I get these low diameter SCCs, and then I get these black DAG edges that all move forward. And then the only edges that can move backwards in the topological order are these that I removed. So those are going to be the problem edges. And again, we want to ensure that there are a few of them, and in particular, we're going to show that the probability of any edge being a red edge is small. Okay, so this is the directed decomposition. Definitely ask me if there are questions about the guarantees, because we're going to be using this over and over and over again. So, 1 second. Sorry, I lost my, okay, good. So in terms of previous work here, the exact result I stated above, we unfortunately couldn't find the black box that gets exactly that. The existing algorithms either work for undirected graphs or they work for directed graphs but are a bit too slow. So they're kind of, everything is not quite what we want. So I think that this particular thing is new and we do prove it from scratch in our paper, but fundamentally the techniques are kind of the same kinds of techniques as in the other low diameter decomposition papers. There are some things we have to refine a little bit. I'm not an expert in the history of these low diameter decompositions, and to some extent we kind of reinvented the wheel. So if you happen to know a lot about them and you look at these guarantees and you're like, I've seen these before, or I feel like these follow trivially from this other paper, then let us know. We would be very happy to hear about that. Okay, so this is the decomposition that we're going to use throughout. So as I said before, the decomposition itself is not, the techniques are very old, but I think what's new about our paper is how we use this decomposition. And in particular, it only works for non-negative edge weights. So the question is, how are we going to apply it to negative edge weights? And to do that, we're going to have this simple definition, which is that we're going to take our graph G and we're just going to round all the edge weights up to 0. So everything that's positive stays the same, but everything that's negative gets rounded up to 0. And we're going to run the low diameter decomposition on this graph with everything rounded up to 0. And we'll see later why that's useful. But for now, I want to point out that there are 3 kinds of edges that result from this, right? There are the edges inside the green components. Those are the type 1 edges. There are the black DAG edges that are between the components going forward. Those are the black edges. And then finally, there are these separator edges that can go backwards. Those are the red edges. And so what our algorithm is going to do is it's going to run in 3 phases, and it's going to one by one fix each type of edge. So basically, phase 1 is going to find a price function such that all of the edges inside the SCCs become non-negative. Phase 2 is then going to find the price function that makes sure that all of the edges, the DAG edges, become non-negative without ruining the edges from case 1. So those are going to remain non-negative. And finally, phase 3 is going to update the price function so that the separator edges also become non-negative. So we have these 3 phases, and I think intuitively, it's pretty clear why phase 2 is going to be easier. Why finding a price function for the case 2 edges is going to be easier than just finding a price function for the whole graph. And the reason is that the type 2 edges are DAG edges, and DAGs end up being super easy. Case 3 is we're going to have to fix the edges in ESEP. And this is going to be easy because there are relatively few separator edges, so they're going to be easier to fix. I think the least intuitive case is case 1. It's sort of unclear. I give you an SEC that has small positive diameter in the positive graph, and I'm somehow claiming that it's going to be easier to compute shortest paths inside that, and it's unclear why that would be the case, especially because the SCC has small diameter from a positive perspective, but it could also have a bunch of negative edges inside it, and negative edges are the hard edges. So the conceptually hardest part is number 1. It's fixing the edges inside each of these SCCs. So let's go ahead and focus on that. So we're going to focus just on the edges inside one SCC. So the recap is we have our graph, we round up all the edge weights to 0 so that we can run our low diameter decomposition. And now we have a bunch of SCCs with weak diameter D, and we're going to focus on one of those SCCs. And our goal is inside that SCC, we want to find the price function that makes all the edges non-negative. And recall that the way to do that is to pick a dummy source and compute distances from the dummy source to every vertex in the SCC. But now we have to compute those distances in the actual graph, not in this rounded up graph. So we have negative weights that we have to deal with. And so the question is, how do we do that? How do we compute distances inside this SCC? And the first observation I want to make, so this is our goal, is this, that for any 2 vertices inside this SCC, we can lower bound how negative they can get. The distance between them can only be so negative. And the proof is really simple. You have these 2 vertices, x and y, and you know that there's a path between them of length at most d. That is the guarantee of the low diameter decomposition. In fact, that pink path is in g greater than or equal to 0. So even after you rounded up all the weights, there's still a path of length less than or equal to d. So now if you also allow negative weights, that path might be even shorter. But for sure, there's a path of length at most d from y to x because they're in the same small diameter SCC. But we also know there's no negative weight cycle in the graph. And so the path from x to y must be at most negative d, because otherwise you'd have a negative cycle. That's the whole argument. So this doesn't exactly get us what we need, but I include it because it sort of at least shows that maybe we're on the right track. That even though we're only applying this low diameter decomposition to the kind of positive graph, to the graph rounded up, nonetheless, it is actually able to give us useful information about the negative distances as well. Unfortunately, this isn't really good enough. What we actually want is to say that every shortest path in the component from the dummy source contains few negative edges, right? We said we have a good algorithm for that case. But unfortunately, the red and the green boxes are not the same. For example, you can imagine that the whole component is just a cycle that's like edge weights 1, negative 1, 1, negative 1, 1, negative 1, and so on. So all the distances are like at most are bigger than negative 1, so they can't get very negative. So the red box is true, But unfortunately, the green box is not, in that you have a bunch of negative weight edges on the cycle, because you have one, negative one, negative one, so you have a bunch of edges of weight negative one. So there's some intuition that maybe low diameter decomposition is useful, but we're not there yet. And so we're going to show a very simple trick that actually gets us the green box that we want. Okay, so that's kind of the setup. And before I show that trick, I want to kind of take a step back and start talking about our actual algorithm. Okay. So our algorithm is, at bottom, a scaling algorithm. So I just want to make sure I because I've never used this, like people can see me, people can see the slides. I just have never used this technology, so I'm just double checking. Okay. Good,
I think everything looks great so far, Aaron.
Okay, thanks. Okay, so our algorithm is at bottom scaling algorithm, meaning this is the main subroutine that we're going to use, which is that we're given a graph with negative edge weights and we make them somewhat less negative. So originally they're bigger than or equal to negative 2b, and we're going to ensure that after our price function, they're going to be bigger than or equal to negative b. So this is really all you need. Once you have this, it's well known that you can get the final algorithm, and it's very simple. So let's say we had this scaling subroutine. I'm going to show that we can solve the problem we actually want to solve, which is you're given a graph, you're given a source S in. This is not a dummy source, this is the actual source. You want to compute a shortest path tree. How do you do that? Well, recall that we assume that all the negative edges are weight exactly -1. You can do that without loss of generality. So all we do is we just call scale down over and over and over again to get these better and better and better price functions, such that at the end, all the weights are barely negative because we've scaled them down so much. They're all like bigger than -1/n². And now all we do is we actually just bump all the edge weights up by 1/n². And so clearly now your edge weights are non-negative. And so now you just run Dijkstra in this graph G star to get your shortest path tree. So we need to claim that the shortest paths in this graph G star really are shortest paths. And this is easy to see. Basically, there are two arguments. The first is that G and G phi have the same shortest paths because all we've done is price functions. So we got to this graph G phi where all the edge weights were barely negative, bigger than -1/n², and that we did just by price functions, so the shortest paths are the same. Now we introduce this additive error of 1/n² to get to G star. But intuitively, in the original graph, all of your distances are integral. So an additive error of 1/n² is never going to change the shortest path structure if originally everything is integral. Because like the total additive error on a path is going to be 1/n. So that's why shortest path in G star are going to be the same as shortest paths in G. Okay, so all of this is just to say that our goal is to get this main scaling subroutine. So let's talk about how to do that. So we're going to need one more key definition, which is that given a graph G, I'm going to define GB by just adding B to all the negative edges. So essentially, if an edge weight is non-negative, we do nothing. It's the same in GB and in G. But if it's negative, then we add B. So it might not be immediately intuitive why this is useful, but we'll see that this is a useful graph to work with. So okay, recall that this is what we want. We want this scaling subroutine. And here is at a very high level how we're going to do it. Instead of working with the graph G, the initial graph, we're going to work with the graph GB. This turns out to be much easier for reasons we'll see soon. Just the simple adding B to all the negative edges just makes our life so much easier. And so what we're going to do is on this graph GB, we're going to be able to compute a price function such that all the edges are non-negative. And now we're going to use that same price function and apply it to G. And if you think about it, if in GB all the edge weights are non-negative, then in G they're bigger than -B, because the difference in edge weights between G and GB is at most B. So if they're bigger than 0 in GB, then they're bigger than -B in the original graph. So the point is just that if we can compute a good price function for GB, a price function that makes everything non-negative, then we're done. Then we can have this scale down subroutine. So the real thing I'm going to have to show you is that working with GB is easier than working with the original graph G. Okay, so let me give the basic framework of how scale down is going to work. This is kind of repeating what I said before a bit. So we have this definition of a graph GB. We have these input and output properties. So the first thing we're going to do is we're going to compute low diameter decomposition. The parameter D is going to change a little later, but basically for some parameter D, we take the graph GB and then round up all the edge weights to 0 so we can apply the low diameter decomposition. And so now we have these three kinds of edges, as we said before. There's the edges inside the green SCCs. So first we're going to find a price function that makes all of these non-negative. Now we're going to apply that price function. So now we have a graph where all the edges inside components are non-negative, but the black and red edges can still be negative. And in the second phase, we're going to fix the black edges, the DAG edges, and then in the third phase, we're going to fix the red edges, the separator edges. And so the point is, at the end of phase 3, all edges will be non-negative in GB. So whatever our final price function is, all the edges of GB are non-negative, and that means that all the edges in G are bigger than or equal to negative B, which is what we wanted. So this is just a recap that we have these three phases. And as I said before, phase 1, I think, is the least intuitive. Like, how are we going to take advantage of the fact that we're working inside these SCCs? Why is that going to be easier? So let me immediately jump to phase 1. And this is why we're going to need GB. It's only for phase 1 that it's really important that we switch to GB instead of G. Okay, so we have this graph GB, and we're in phase 1. So we ran this low diameter decomposition, and we're going to focus on a single SCC in that decomposition. And we want to compute a price function for that SCC. And remember, the way to do that is we're going to want to compute distances aside the SCC. So we're going to add a dummy source, and now we just want to compute distances from the dummy source to every vertex inside this SCC in the graph GB. So first off, this is a repeat from what we know before. We know that for any two vertices, the distance between them, the most negative it could get is negative D. Because we know there's a path from Y to X of length less than or equal to D by the low diameter decomposition. So since there's no negative weight cycle, there's a path from X, the path from X to Y has the most negative it can be is negative D. Okay, and now I want to claim something that we actually have the second property we wanted. I want to claim that in fact we can say the following, that if you have your dummy source, then for any vertex Y, the shortest path from the dummy source to Y has at most n over 2 negative edges. So in an arbitrary graph, it can be n negative edges, and we're actually showing that no, there's a limit on how many negative weight edges you can have. So it's just an algebraic proof. It's a little hard to do algebra on the board though, so I'll try to walk through this slowly and stop me if there are questions. So, okay, we have our dummy source S, and we want to show that the path from S to Y in GB uses few negative edges. I don't know if you can see, but on the black path, that's the path from X to Y. We have these little red edges, and we want to prove that there are only so many of these red negative edges. Okay, so first off, the path from S to Y, right? S is a dummy source, so the first thing it does is go to some vertex in the graph, and then just takes a path in the graph. So it's always like you go to some vertex X, and then you take the path from X to Y. So let's think about this path from X to Y. What do we know? Well, one thing we know is that the path from Y to X, this orange path, has length at most D. Again, it's a low diameter decomposition. It has at most D even when you rounded up all the edge weights, even in GB bigger than or equal to 0. So certainly in GB, where all the edge weights are even smaller, that edge weight is also going to be at most D. So the orange path is at most D, which is equal to NB over 2. On the other hand, we know that the black path in GB has weight at most 0. Why? Because S is a dummy source. And this is the place where we really want to use that S as a dummy source. Right? There is an edge from S to Y of weight 0 because S is a dummy source. So any path we take is definitely going to have weight less than 0. So this path from X to Y has negative weight, or at least non-positive weight. Okay, and now we want to talk about the number of negative edges on this path. And basically what I want to claim is this, is that if there were too many negative edges on this black path from X to Y, then although the weight in GB might be around 0, the more negative edges there are, that would mean that the weight in G is very negative. But the weight in G can't be too negative because otherwise you would have a negative weight cycle with the orange path. So the argument is just this, that the weight, let's focus on any particular red edge. If that edge is negative in GB, that means that it was negative in G. And that means that the weight in GB and in G differ by a factor of exactly B. Right? If it was negative in G, then we added B to get the GB. So basically, for every red edge that's negative in GB, the weight of that path in G drops by B. So if the weight in GB is less or equal to 0, then the weight in the original graph G is less than negative B times the number of these negative edges, negative red edges. And by negative red edges, I mean edges that are negative in GB. But this basically completes the argument because we know there's a negative weight cycle. So we know that if you take the orange path, which is NB over 2, and then add the weight of this black path, which is negative B times the number of negative edges, that should be positive. And so rearranging, we get that the number of negative edges on the path is at most n over 2. So the point is that in GB, if you look at any vertex y and the dummy source, the shortest path contains at most n over 2 negative edges in GB. And what that means is that we can run our algorithm that works well as long as there are a few negative edges. So we've proved this green box. And the question is, what do we do now? And the answer is, well, we know that the distances are going to be easier to compute because we have fewer negative edges, so we can just run Bellman-Ford plus Dijkstra. The issue, of course, is that, yes, it'll be easier. Instead of having n negative edges, you have n over 2 negative weight edges, but n over 2 is still too many negative edges. I mean, Bellman-Ford plus Dijkstra will still be slow. And so the solution to this is to use recursion. So we've shown how to halve the number of negative edges, and you just keep doing that. You keep halving the number of negative edges until you have very, very few left, and then you can use Bellman-Ford plus Dijkstra. So now I have to introduce basically the last change to our framework, which is that the whole thing is actually recursive. So let's go back to the algorithm scale down. And now we're going to introduce a recursive version where delta is going to basically be the parameter that keeps track of progress inside the recursion. So the input is the same as before. All the edges are weight bigger than or equal to negative 2b. But there's also an additional requirement, which is that in GB, all shortest paths from a dummy source have at most delta negative edges. I'll give an equivalent definition. If instead of thinking about GB, you want to think about G, what this is saying is that in G, all shortest paths from a dummy source have at most delta edges that are very negative, right? If an edge is only slightly negative in G, then it'll become positive in GB. But if it's very negative in G, then it'll still be negative in GB. So this is basically saying that there are few very negative edges in the original graph, and so there are few at all negative edges in GB. That's what the delta is measuring. And the output is the same as before. We're going to scale down all the weights. Okay, so how do you do this? Well, I guess before saying that, so this is the recursive function. For the initial call, you can always just call it delta equals n. Delta equals n is always valid because there are at most n negative edges on any path. So the top level call would just call it with delta equals n. And let me also talk about how to do the base case, which is if delta equals 1, this problem is really easy. Because delta equals 1 means that every shortest path from the dummy source has almost one negative edge. So BF plus Dijkstra is going to be super fast because you have few negative edges on the paths. So you run BF plus Dijkstra, you set the price functions to be the distances, and as we've said before, once you compute distances, you get a price function such that all the edges become non-negative. In GB, right? We can only run BF plus Dijkstra in GB. That's really important because our guarantee is that in GB there are a few negative edges, and that's why BF plus Dijkstra will be fast. In G there might be many, many negative edges, but in GB there are a few, and so we can compute distances, so we compute a good price function for GB. And then the point is that in G gives you a price function where all the edge weights are bigger than negative B. Okay, so we have the initial call, we have the base case, and now we have to show how to compute this recursively. So let's kind of slowly work out the pseudocode phase by phase. Okay, so we have, this is the final algorithm we want to solve. We have our input and our output. And another part of the input requirement that I'm writing is that every shortest path in GB contains at most delta negative edges. Okay, so the first thing we do is we call this low diameter decomposition. Sorry about that -0, that should just be 0. So we're just taking the graph GB, we're rounding up the edge weights, and we're calling low diameter decomposition. So that's this thing here. And now we said we work in 3 phases, right? Phase 1 takes care of edges inside the SCCs. Phase 2 is going to find the price function such that all the black edges become non-negative. And finally, we find the price function to make the red edges negative. And we said that once we have this, all the edge weights will become non-negative in GB, and so they'll be good in G. Okay, so now now we are ready to actually do each phase properly. So let us start with phase 1, the hardest phase. And see, now phase 1 has become easy. So again, we're going to focus on a single SCC after we do this low diameter decomposition. And the parameter now is delta B over 2. And I claim right away that what we know is that for every vertex, the shortest path in GB has at most delta over 2 negative weight edges. So think about it this way. In the initial call, our setting delta promised that every shortest path has at most delta negative weight edges. But now we're saying that inside each of these components, you can say something stronger. You can say that the number of negative edges has dropped to delta over 2 instead of delta. And the proof is exactly the same. I'm not going to redo the algebra. Before I had n over 2, because of how we set this parameter d, we set it to nb over 2. Now we set it to delta b over 2, and all the algebra goes through exactly as before. Okay, so we know that inside each component, you have at most delta over 2 negative weight edges. And so what do? You just call scale down inside each component. But now you get to improve this delta factor from delta to delta over 2. And that's it. That solves the problem. So this is the algorithm for phase 1. Okay, so if we go back to the pseudocode, this is the algorithm for phase 1, where our goal is to make sure that all of the edges inside SCCs become non-negative. So what we're going to do is just inside each SCC, we know that the number of negative edges has decreased. And so we can run scale down with the smaller delta parameter. Okay, so that's phase 1. Now let's talk about the other phases. So before doing that, let's talk about the recursive running time. So phase 1 is the only recursive step in the whole algorithm. And it's going to be easy to see that the non-recursive work is near linear. So essentially what's happening is that to run scale down with parameter delta, you need to do near linear non-recursive work and then call scale down with parameter delta over 2. So it's pretty easy to see that you only have log n calls. So the overall running time is still going to be near linear. Okay, so we've settled phase 1. Now we're moving on to phase 2. So let's think about, by the time we get to phase 2, we've run phase 1, we found the price function, we applied that price function to our graph. So what that means is that we have a graph where all of the edges inside SCCs are now non-negative. But in this graph GB minus ESEP, you can still have these forward DAG edges that can still be negative. And so now our goal is to adjust the price function so that those edges also become non-negative. So let's do that in phase 2. So again, we have all of these SCCs in our graph, and we want to set the price function so that the edges between components become non-negative. But we also want to make sure that the edges inside, the edge weights inside components do not change, because we made sure that those are non-negative through phase 1, and we don't want to ruin all of that work. So we're going to set the prices in such a way that we just don't change the edge weights inside the components at all. Okay, so phase 2 is actually by far the easiest phase. It's just like a little bit of kind of numbers, so it can be hard to parse, but this is conceptually the easiest one, where I'll just put up the picture right away. So we have these 3 components, and the black numbers are the original edge weights. So just focus on the black numbers for now. What we're going to do is we're going to go through the components in topological order. And when we're done processing a component, we're going to ensure that all of the edges entering that component have become non-negative. So we start with C1. There are no edges entering C1, so there's nothing to do. Now you move to C2. So the goal is to set prices so that all of the edges entering C2 become non-negative. So all you do is you find mu2, which is the most negative edge weight entering C2. That's -8. So you want to increase all of the edges entering C2 by 8, and then they'll all become non-negative. And the way to do that is just you set the price of C2 to be -8, meaning you set the prices of all the vertices inside C2 to be -8. And then if you think about it, any edge entering C2, well, it's coming from C1, so the reduced edge weight is the original edge weight plus phi of C1, which is 0, minus -8. So that's the original weight plus 8. So we're adding 8 to all the edge weights. 8 was the most negative edge weight, so now they've all become non-negative. And the other nice thing here is that the edges inside C2 haven't changed at all, because we're giving every vertex in C2 the same price. So every edge inside C2, you'll just add -8 and then subtract -8, and the edge won't change. Okay, now we go to C3. Again, now we want to make sure that all the edges entering C3 become become non-negative. And the way to do that is look at the most negative edge weight entering C3. So in this case, that's -6, and add it to the price from the previous component. So you had -8 before, you add in -6, you get -14. So now we're going to set all the prices inside C3 to be -14. And again, you can see that all of the edge weights entering C3 have gone up by 6, or at least 6. Because any edge from C2 to C3, you take the original edge weight, you add phi of C2, which is -8, but then you subtract -14, so you've increased it by 6. 6 was the most negative edge weight, so everything becomes non-negative. You could also have edges from C1 to C3, but for those you add even more than 6, right? Because C1 had an even smaller price, so you're adding at least 6 to every edge entering C3, so everything becomes non-negative. So that's the whole algorithm. You just go through and fix one component at a time. Okay, so that's phase 2. We have fixed the DAG edges. So let me now move on to the next phase. So first I'll fill in the pseudocode. So we have our algorithm, we filled in phase 1, and now we're saying phase 2, this is the algorithm. To make all the edges between SECs non-negatives, you compute the SECs in topological order, and then you just sort of loop through the SECs and adjust prices as you go. So now our final step is phase 3, which is that we now have to make non-negative these backwards edges in ESAP. So let's talk about phase 3. So by the time we enter phase 3, we have computed a price function such that all of the edges inside the green components and all of the black DAG edges are now non-negative. Everything is non-negative except for the red separator edges. So we really have very few negative edges left. And moreover, we know there are few of them because we know that every edge is one of these red edges. We know the exact probability with which that happens, or we know an upper bound. So it's at most the weight of that edge divided by delta B. Okay, so now our final goal is to actually compute a price function so that all the edges are non-negative. And to do this, I want to hark back to something I said a long time ago, which is that we had this intermediate goal where we said, what if we could find a price function where there might be negative edges, but on average, the number of negative edges on a shortest path is small. And I claim that actually we have already found that price function. This price function that we start phase 3 with, where all the edges inside components and all the black edges are already non-negative, that's exactly this intermediate price function. In particular, I'm going to prove that in this graph, the number of negative edges on any shortest path is small, or on the average shortest path is small. And the reason is pretty intuitive, because at this stage, the only edges that can be negative are the red edges. But we know that every edge is a red separator edge with a small probability. And so on any given path in expectation, you're going to have few of these separator edges. And so you're going to have few negative edges. Okay, let's do that a bit more formally. How am I on time? I can sort of skip the algebra here. So do I have like 10 minutes, or it says session ends in 6 minutes? Yeah, I don't know how literal that is.
I think let's assume we can go on for longer. Ming, can you confirm this? I think we don't get kicked out if we don't want to. All right, I think Aaron, let's continue. I think this should be okay. But
okay. I think I'll go like 5 minutes over at most.
Yeah.
Okay. So So in particular, what we want to prove is that we have this algorithm, df plus extra, right, which works well if you have few negative edges on average. So we want to show that every shortest path on average has few edges from ESEP. And ESEP are the only negative edges because we've already fixed all the other negative edges. So as long as we can show there are few edges from ESEP, we're done. How do you prove that? Well, this is just repeating what I said of why this is good enough. So if you have these, if you know there are a few edges from ESEP, you know there are a few negative edges, and then you run BF plus Dijkstra to compute actual distances. And once you have actual distances, you get a good price function. So now we have to prove this claim. So here's the claim. We want to prove it. And the proof is pretty simple. So we have our graph, we have our path from S to V. And so note that we know that the probability that an edge is a separator edge depends on the weight of that edge divided by delta B. But we ignore negative edges. There's no way they're separator edges. So basically, in total, the total number of separator edges is going to be proportional to the positive part of the path. Basically, if you break the path up into negative edges and positive edges, all of those positive edges have a chance to become separator edges. So effectively, we want to bound what is the total length of all the positive edges. So we're going to decompose into positive and negative, and we want to bound the positive weight. So we know that the intersection of the path with ESEP by like this recall statement above is precisely the positive weight divided by delta B. So how do we bound the positive weight? Well, we know that the original weight, not the positive weight, the total weight, is less than or equal to 0. Because again, it's a dummy source. Like you could always take a path of length 0. So the original path is less than 0. So basically what I'm going to do is I'm going to show that the negative part can't be too negative. And that immediately shows that the positive part can't be too positive because together they're less than 0. And to see that the negative part can't be too negative, it's actually just definitions. By definition, the shortest path from S to V uses at most delta negative edges on the shortest path. And each of those has weight bigger than negative B, right? In the original graph, all the edges have weight bigger than negative 2B. That's the input to scale down. And so in GB, since we add B to all the negative edges, all the edge weights have weight bigger than negative B. So there are most delta in the negative part of this path. We know that there are most delta edges because that was the input to scale down. There are most delta negative edges, and each one has weight bigger than negative B. So the most negative the negative part can be is negative delta B, which means that the positive part can be at most delta B. And so that's it. The positive part is at most delta B. You will, again, apply this probability bound, and you get a constant number of separator edges in expectation on each path.
Aaron, sorry to stop you. So I think I just found out that we might indeed have that the recording will stop, and we might kind of have a short interruption where people have to click to go back in, and then I think we can take questions after.
I see. So should I basically have a few minutes of summary? Should we do that now, or should I just keep going?
Now, and then I think we can continue after, but the recording will stop, and we might have to click a button to get back.
Okay, got it. Okay. So let me just give, I mean, we're done, basically. So this was the for phase 3. And now to just give the whole pseudocode for scale down, the framework was that we have these 3 phases. We do low diameter decomposition, and then we successively fix all the different edges. And here was the full pseudocode. I'm not going to repeat it. I'll just put it up, maybe just so you can see it. Okay, so this is the pseudocode. And now I'm just going to quickly do kind of open problems, summary of our results, that kind of thing. So one thing I want to say first is once we have this algorithm scale down, let's recall that this immediately gives the final algorithm. Right? You just keep applying scale down over and over again until your edge weights are barely negative, and then you bump them up so that they're not negative. So scale down is really all we need. Okay, so we showed how to do the scale down subroutine. So let me just end by giving a summary and open problems. So the summary is that for negative weight shortest paths, we have an algorithm with running time m to the log eighth. Good. Can everyone see the screen?
I think we have it again now. Yep.
Okay. Anyway, we're just like 2 minutes from ending. So as I was saying, result, I think we can optimize log factor. So getting to something small like log squared or log cubed is interesting, and I don't know within our framework. So let me just quickly review this. Basically, there were these classic algorithms, and then there was this combinatorial improvement in the 80s and 90s, and then there's this very recent work using continuous optimization and dynamic data structures. And so an interesting thing about our result is that we don't need this more recent machinery. We're able to just kind of use the more basic tools from the 80s and 90s to get this improved runtime. So let's talk about open problems. So first I'll talk about open specifically in negative weight SSSP. There is a really big open problem, which I have absolutely no idea how to even approach, which is that all of these algorithms are scaling algorithms. Like if you want a strongly polynomial algorithm, the best is Bellman-Ford from the 50s, and no one has any idea how to do better, I think. So that is a big open problem. I don't know if there might also be conditional lower bound suggesting this is not possible. I'm not sure. So there are also some more minor open problems. For the case with scaling, we've mostly settled the problem, but there are kind of two things. One is I kind of mentioned that I think one nice thing about the fact that we're kind of using more standard combinatorial tools is it's the sort of tools that one could be able to port into the distributed or parallel models. So for example, in the congest model, although there's a lot of work on shortest paths with positive weights, I don't think anything non-trivial is known for negative weights. And so it'd be interesting to extend our result to that model. We haven't looked at it too much, but I think there's a decent chance that some of the ideas can be used. In particular, in some sense, like the most like technical part of our result ends up being this black low diameter decomposition. But that low diameter decomposition was developed in the distributed model, and there are a bunch of really fast distributed algorithms for it. So that's going to port really easily. Okay. And then finally, we'd like to reduce the log factors to something more. Again, a few log factors we really didn't optimize, and they'll be easy to reduce. They were just for simplicity of presentation, basically. But I think something like log to the fifth is inherent in our current framework, and it would be nice to go lower. Okay. And then I also want to kind of mention again that sort of in some ways see this result as maybe, hopefully, kind of one result in a larger agenda, which is basically take some of these fundamental graph algorithms that have been around for decades and that we cover in undergraduate algorithms, but the only way we know how to solve them is using complex machinery, and try to develop simpler algorithms for them. And I think we have kind of made the first step in that direction in a while with negative weight shortest paths, showing that actually these problems, maybe it's worth revisiting them. Maybe we can get simple algorithms. But of course, we only got it for negative weight shortest paths. I have no idea if it's possible to get it for these other problems, but I think that'd be an interesting direction to look into. Probably the next problem to look at is bipartite matching. Just because it's the simplest remaining problem on the list, it's like a really fundamental problem and has such a nice, simple definition that it feels like maybe there's a simple algorithm. It also hasn't seen like any progress on the combinatorial front since 1973. So I think it would be interesting to see if we can, even if not get near linear, at least beat mRoot-N using kind of more traditional, like simpler combinatorial tools. And yeah, that's it for the talk. Thanks all for inviting me.
Thank you so much, Aaron. It's absolutely full stuff. And the audience we can't hear them, but they can click the little clap button.
Okay, great. Thank you.
Thank you for a very nice talk. Maybe let's see if we have some questions. People type them into the or one, they can raise their hand and we can turn it on as well. So people in the audience. Maybe while people take their time to think about the questions, I'll ask what changed in to make it nearly versus an earlier version was almost linear.
Okay, so I think that I remember the details of the previous version. I just don't remember it. So, second. Some of the previous versions are undirected, and the directed case gets more complicated because you can't, like, once you compute a ball in the undirected case, you kind of are done. Like, if you ball and you cut at some threshold less than d, that's it. That ball is small diameter. But in the directed case, you have to work in both directions, and so you can have cases where like the balls are large in one direction, small in the other direction. So you have to be careful when you do these things. So that is kind of, so there was a near linear time undirected algorithm, and I suspect many of that, like one could probably do our result using more of their techniques and maybe get it to work, but it doesn't work directly because the graph is direct. We also had a paper on the directed decomposition in a previous paper on dynamic algorithms with Max, actually, who probably is in the audience, but I can't see who's in the audience, unfortunately. But
yeah, Max is here indeed. Yeah, sorry.
Yeah. So I'm trying to remember that algorithm. I think the ideas from that algorithm were on the way to near linear time. So that algorithm didn't get near linear mostly because it worked in a dynamic setting, and so it had to do more. So essentially, like what that algorithm did is, I'm trying to think how to explain this in a not too technical way, but it sort of picked the source, and then to get this ball of small SCC, it would try to prune away everything around it, and it would actually use a dynamic subroutine to do that. So it would kind of prune some things away, and that might change distances from the source a little bit, but that would all be kept track of by a dynamic algorithm. And so this was good because it allowed everything to be dynamic, but dynamic algorithms are slow. And so we needed a way to do that that doesn't try to like maintain the source dynamically. And so instead we kind of showed like a more streamlined way where you kind of prune things without really updating the distances, because you only care about weak diameter, everything works out. That's sort of the short answer.
Yeah. Maybe Goran will ask another.
Yeah. Thanks. Mm-hmm. Exactly. Mm-hmm. Great. If I can go back to the basic picture. I promise you, if you if you look at somehow, it's just using Bellman-Ford plus Dijkstra. There's nothing fancy going into it, but let's see if I can talk through the proof a little bit. So, 1 second. Okay. So basically, the idea is that so one thing you could do is you run update every label. Then you do one iteration of Bellman-Ford, you update every label. And now from all of the new labels, you run Dijkstra again, right? So you can seed Dijkstra with whatever labels you want. So if every vertex has an original starting label, you can just run Dijkstra from those starting labels. So this is to get the basic version. If you know that everybody has at most k negative edges, then you just sort of run Dijkstra from all the labels, then update all the labels with one iteration of Bellman-Ford, then again run Dijkstra from all the labels and do this k times. But the key thing is that if you think about it, if a vertex, let's say you do a Bellman-Ford iteration and the distance to some vertex v did not change. So you did Dijkstra, you have your new labels. Now you do a Bellman-Ford iteration and the label to a vertex v just didn't change at all. Then you don't have to incorporate, when you run Dijkstra the next time, you don't have to incorporate that label. You can you don't have to sort of put it in the queue at all. You can just skip it. I mean, right, maybe that vertex will be affected by something else, and then obviously you will end up putting it in the queue, but by default, you don't put it in the queue. And so the point is that to any given vertex, let's say that a particular vertex v has like k of v negative edges on the shortest path, then after k iterations of Dijkstra and Bellman-Ford, you will have the final label for that vertex. And so that label will never change again, and you will never ever see that vertex again. You will never add it to the queue ever again. So basically, each vertex end up being processed a number of times equal to the number of negative edges to that vertex. So, yeah. And yeah, and this is, by the way, why we needed constant degree. I mean, there are other ways to phrase it, so you don't need constant degree, but if you want this phrasing, you need degree because basically we're saying that if a vertex is explored k of v times, if a vertex has k of v negative edges, then it's only explored k times. But it would be bad if somehow there were a few vertices that had many negative edges to the path, but also those edges had very high degree, because then those vertices, exploring them would be very expensive. But this way, we're kind of ensuring that you pay a uniform cost for all vertices. That's why we assume constant degree. Yeah. And again, this is without loss of generality. You can convert any degree to any graph to have constant degree. So I see a question in chat. So by Simon. So should I go ahead and answer that?
Yeah.
So Simon, or I don't know how to, so Simon, I'm not sure how to pronounce your name, but so essentially it is definitely weak diameter and we never need strong diameter. So we need this requirement that the path has length at most d in the graph, not necessarily inside the component. And to see that this is enough, the only place where we need this diameter bound is in this claim about phase one. Like this is an example where we're saying that the path inside the component from x to y has length bigger than or equal to negative d. So here we're making a claim about this black path. The low diameter SEC decomposition ensures that there is this pink path. And this pink path might leave the component. We're ensuring that there's a pink path of length at most d. That pink path might leave the component. But the point is that even if the pink path leaves the component, we know that this black plus pink path forms a cycle in the graph as a whole. And we know that the graph as a whole has no negative weight cycles. So if the pink path has length at most d, then the black path has length bigger than or equal to negative d.
Great. Hey, Aaron, maybe I can also ask a question. So
yeah,
maybe I'm circling back a bit to what Rasmus asked. It's basically, do you think there's like an even simpler version, or like put differently, like how would you teach this? Would you basically go to a undirected graph and then really try to get it there? And is there like a two-layer version or something like that where you only recurse like a little bit before you go full on, or do you think the...
I see. Do you mean for the low diameter decomposition, or do you mean for the algorithm as a whole?
I think for the algorithm as a whole, like you kind of do the low level decomposition, and then maybe you only do it 2 levels or something like that. Will that already get me to like m third root of n?
It would. I'm not sure the extent to which just using 2 levels would be that much easier is the main worry. Like at some point, yeah. I think, so in the kind of original paper, which is n to the 1 plus little o of 1, which we put up on archive and later improved, that was a little more complicated. There we kind of showed 1 level to get m square root n, which m square root n wasn't new, but it was like a totally different way of getting m square root n. So I think that I do think it becomes a bit simpler if you do it for m squared n, because then you still have to do a scaling algorithm, but you no longer have to make it recursive. Basically, just like at the top layer, you have n negative edges, and then if you set parameters appropriately, at the next layer, you have root n. Like then inside each component, you have root n negative edges, and then you just run bf plus Dijkstra. So I think that would be the easiest way to do it. That way you skip the recursion entirely.
Yeah, I think that sounds very teachable, because I think the algorithm as is now is like very simple to experts, and I think it's like on the brink of being teachable.
I agree. It's
like,
gray zone of like, yeah.
It's kind of, especially the recursion, you have to think quite hard about like what you're recursing on and how that interacts.
Right.
Yeah. But I think with that like two-level scheme, or like the scheme that you described, that is actually really, really simple. I think that can be taught like very well.
Yeah, that's the hope. I think, to be honest, the least teachable part right now is the low diameter decomposition. And I think partly we did not focus on we focused really hard on trying to get the rest of the algorithm as simple as nice and possible. And we didn't really do that for low diameter decomposition because our result is barely new. So I suspect that what we're doing in our paper is too complicated. I think our goal is at some point to actually read through all the literature and find the actual right way to do low diameter decomposition. I think the hard part is that many of the existing algorithms for low diameter decomposition are a bit complicated because they're in the distributed setting or the dynamic setting. I suspect that since we only care about the sequential setting, there could be an actually easy way to do low diameter decomposition, but we never actually really bothered to do that. We just kind of ported the dynamic algorithm over. So I would like to see a simpler version of that, but we don't have it.
But isn't your algorithm basically implementing MPX?
What is MPX?
Yeah, okay. Maybe we can talk about this offline, okay. Because I think that would actually be the easiest way to describe what you're getting, and it's basically what you're doing, I think.
Yeah, I think so, but it ends up being surprisingly I feel like when you describe the low diameter decomposition, it's simple, but it is it's almost as long as everything, our whole. I think it's longer than our whole algorithm. If you just take the technical part of our algorithm, the low diameter, because there's still a lot of I don't know, weird conditional probabilities that show up and stuff. So.
Yeah,
I would like to see a better way. Yeah,
that's good.
So I think we still have time for another question if anybody wants to, and also we have this option to join kind of a little chat afterwards. I don't know if you have a minute, Aaron, to.
I do, sure. Yeah, that sounds great.
Yeah, so then people can also ask Aaron more things there. But if anybody wants to get a last question in. Okay, so then let's all thank Aaron again, and you're all very welcome to join these tables afterwards.
Will someone walk me through how to do that? I feel like I'm going to get lost in this online world.
We'll get kicked out in a second.
Okay. All right. Well, thanks everyone who isn't able to make it.